I will have a voltage source that will be like so, like so, like so, like so. I will have a resistor, another resistor, ground in this case, another resistor, and I'm going to do this source this way. I'm going to make this guy 12V. I'm going to make this guy 7V. I'm going to make this guy R1 at 100 ohms, make this guy R2 at 200 ohms, and make this guy R3 at 300 ohms. All right, and you are asked to do a VIR for R1, R2, R3, and you need a V, you need an I, and ultimately you need an R. At the end of the exercise, this is what's required, all right? Now, in order to do this, there were a couple of basic steps. First of all, can you use series aiding and series opposing on this exercise? Nope, because they're not in series with each other, and they're not in parallel with each other. They're not series, so you can't do series aiding or series opposing. This is positive, this is negative, this is negative, this is positive. We don't know what else is happening here. So step one, step number one. Let's see, let's call this one VS1 and call this one VS2. So in the first step, what you have to do, you have to replace one of the voltage sources. So replace VS2 with a wire and solve for all currents and directions of currents. That's your task.
Professor, are we replacing V2 because it has the smaller value?
No, it could have been VS1. I just happened to pick that side of the circuit.
Okay.
It mattered not which one you start with, because you're going to, in the second step, you're going to reverse the process, okay? So it matters not which one we start off with. What does matter is we follow a very methodical process of how this is done. And the methodical process of how this is done is this way. So what we're going to do is we're going to replace this guy with a wire, which means I have to redraw this. So that's all right. Here, 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 here. This guy, this guy, this guy. And replace this guy with a wire. Okay, now it's replaced with a wire. My R1 is here, it's still 100 ohms. My R2 is here, still 200 ohms. My R3 is here, 300 ohms. And I have a 12-volt source, which is my VS1. Based on this, can I simplify this network of resistors from 3 resistors down to 2? How can I do that? Can I redraw this? What relationships do we see? Parts of this are in series, parts of this are in parallel. Oh my God, what am I going to do? Where's my reference? My reference is going to look at the voltage source, and where do I start my analysis?
Farthest away.
Farthest point away from the source. So I'm going to start over here. If my voltage source is here, I'm going to start here. And I'm going to look back into this. What do I see as this wire? What's on this wire? R3. R3 attaches at node A, and R3 attaches at node B. What else do I see? What am I going to combine here? Question goes to Erica. What am I combining?
Sorry, can you repeat the question again?
Sure. I have a series parallel circuit with one voltage source replaced by a wire. Now I only have one voltage source, 3 resistors. How do I simplify this on my way to RT?
I'd use the reciprocal method to combine resistor 3 and resistor 2.
Mm-hmm. In other words, you saw that they are in parallel with each other, yes? you saw that this guy is, let's go ahead and do this. This will be an REQ1, and that's R2 in parallel with R3. And you use reciprocal to do this. So everybody calculate the reciprocal of these two numbers right now. Don't wait for me to do it. Pull out your calculator, lay it down, and do your reciprocal calculation. 200 reciprocal, on this calculator here, plus 300 reciprocal equals reciprocal. I'm not going to hit equals yet because I want the number from somebody.
120.
Abbas, what do you got?
120
120 what? Apples, oranges, cats?
ohms.
Oh, okay. All right. So we need something more than a number always, right?
Right.
And it is 120 ohms. Is everybody good with that? All right. My R1 is here, 100 ohms, 12 volts, VS1. Do I have enough information to calculate an R total? Class, are these two in series? So my R total works out to be what value, Ephraim?
Give me 1 second. Sorry, I went to the restroom.
Hang with me, people. It's a simple series circuit, 2 resistors. In series, these add up to be what value, Harpreet?
220.
220 what?
220 ohms.
There you go, 220 ohms. You don't need a calculator for this. Mama's calculator, right? 100 plus 120 in series is 220 ohms. Done. Do we have enough information to do a partial chart? And this partial chart, we only want certain things for R1, for R2, R3, and totals. We only want certain things. I need a current and I need a direction and maybe an R value here. So R was 100. R here was 200. R here was 300. What's my R total? My R total is 220 ohms. Yes, these are all ohms. I ran out of space. Sorry. Do I have enough information to determine total current?
Yes.
We don't have to worry about filling in the V column yet. The V column is superfluous at this point, but I do need this information. So what's 12 volts divided by 220, everybody? 12 volts divided by 220. Question goes to Frank. What is 12 volts divided by 220? Sepulveda. Go ahead, try that again. Are you still driving, Frank? Ephraim, what do you have?
I got a 54.55 milliamps.
Okay, so my IT equals VT over RT is
Correct.
equal to 12 volts over 220 ohms is equal to 4.55 milliamps. Is everybody okay with that current? Done. Okay. Take off your microphones, everybody. Because if you have any background noise, you'll take over the screen and people won't be able to see the circuit. Is everybody okay with 54.55 milliamps? Once you have this, now on this simplified circuit, you're going to analyze what's happening between these two guys. Current comes down here, comes up here, flows up, flows over, through here. In this simple circuit, what question do you ask yourself? The question is, does this current flow through any original circuit resistor, yes or no?
Yes.
Yes, it does. Which resistor does this 54.55 flow through? Which original resistor does it flow through in this simple series circuit?
R1.
R1. So now do we know the total current is 54.55, oops, I wrote it in the wrong place, 54.55 milliamps, and it is the same current that flows through R1, so 54.55 milliamps. Are we good with that? How about the direction of current through, R1? Is that up, down, left, or right through R1?
Left.
Flows to the left. Is everybody okay with that? So far, so good? Next, how do we reconcile, oh, that we're done with the series circuit. There's no more to analyze on this that helps us here. In order to find the currents that flow through R2 and 3, we have to take this information back to this intermediate circuit here, our first redraw. We took out the voltage source. We happen to have these two guys in parallel with each other. So current flows down here, over to here, over to here. We said the current comes back to the right. What happens at node B with this current? Doesn't it split to go up? And doesn't it split in this direction? So what is the direction of my current going up through R2? It's up, yes? So R2's current is up. How about the current going through R3? Is it up, down, left, or right?
Left.
Jess? Flows to the left. So we now know these two directions. Now we just need to know what are the amounts. How can I find how much current flows in each of these branches? There's a couple ways we can do this. If we stay with currents, we would use current divider, yes? If you stay with current, you would use current divider, but you don't have to just stay with current. You can do this a couple of different ways. But what would my current divider look like? Remember, I happen to have 54.55 milliamps flowing in this direction, running into node B. And then it splits in two
You want to
paths.
pull it a little up, Professor?
Yeah, thank you. And it splits into two paths to come back out. 54.55 milliamps coming back through R1. So how do I determine how much current goes through each of these? I have a parallel relationship. So your current divider, CDF, current divider, IR2 is equal to REQ1 over R2 times I total, yes? What was my REQ1? Well, how come the general form of the formula shows RT? Why am I using REQ1? How come I'm not using the R total of 220?
Because the current's been divided.
RT is for the entire circuit. The T in the current divider formula, if you recall, IRX is equal to R total over RX times I total. That's the general form of the formula, but we don't use RT for the whole circuit. We don't use the 220 ohms. We only use the RT for the couple of guys that are in parallel. And we already deciphered that as REQ1. So this is going to be equal to 120 ohms over the value of R2, 200 ohms, and multiply this by 54.55 milliamps. So that's my equal to IR2, and my IR3 is equal to REQ1 over R3 times I total. So that guy is going to be equal to 120 ohms over 300 ohms times 54.55 milliamps. So that's how we calculate the current for IR2 and the current through IR3, is using current divider formula. And if you do this correctly, let's go ahead and generate some numbers here. 120 divided by 200 times 54.55 works out to be what value of current? Question goes to Luis. Do you happen to have this yet?
Luis had to go.
Oh, he had to go. Okay. Exponent -3. All right. Question goes to Harpreet. Do you happen to have this current yet?
Yes, 32.73 milliamps.
32.73 milliamps is correct. And now we do the same simple math. 120 divided by 300 times 54.55 milliamps. So on my calculator, divide by 300 times 54.55 exponent -3. And the question goes out to Erica. What do you calculate for the current going through the second branch? Jess, do you happen to have that number?
Sure do. 21.83 milliamps.
21.82 milliamps or 83 milliamps. All right. Let's see if these numbers make sense. Does the higher current flow through the smaller ohms of 200? Does the smaller current flow through the higher ohms of 300 ohms? In other words, the smaller ohmic branch, does it have the higher current? Does the higher ohmic branch have the smaller current? So yes, we have proportional distribution. We're happy with this. Let's go ahead and fill this in. 32.73 milliamps, and then you have 21.82 milliamps. And this is all you need for this step. For step 1, our goal is to get this information on a table: total current and directions. We don't have to calculate voltages. We really didn't have to write down ohms, but we did need an R total. So the most important parts of this particular guy, you need an R total, you need an I total, here, here, here. Those are the critical components that we're going to save for the next step. Everybody okay with step number 1? Okay, so for step number 2, return VS2 and replace VS1 with a wire and solve for currents and directions. Solve for currents and directions. The original circuit, that's your step 2. We've got to return the VS2 of 7 volts, replace VS1 with a wire, and solve. So it means we're going to have to do some drawing. So in this particular step, we're going to, my R1, 100 ohms. Here's A. My R2 of 200 ohms. I'm going to have a VS2 of 7 volts. Point B, ground. And then on this side where VS1 was, I'm going to replace VS1 with a wire. Oops, missed one. Sorry, got too excited. So my R3 of 300 ohms. Is everybody okay with this step? On my original circuit, I bring back VS2, 7 volts, and it was, as I've originally drawn it, negative on top, positive on the bottom. Replace VS1 with a wire. I've replaced it with a wire, and all the resistors remain in the same place. Now I have to solve for this guy. I have to do a redraw. I want to take this guy down to an R total. So what combines with what in order for me to do my redraw? Question goes to Ephraim. Tell me what combines with what?
So we now do use the 100 and 200 parallel first, and then
Is
we
Good.
yes.
Is everybody okay with these two guys being in parallel? Remember, if the voltage source is here, you look at this particular part of the circuit looking back in, and can you see that R1 and R2 are in parallel with each other? Hopefully you can. And so I have a point A right here. I have a resistor right here, a voltage source right here. My R3 is 300 ohms. This is my VS2 of 7 volts. And I happen to have right here an REQ1, which was equal to R1 parallel with R2. This is equal to 100 parallel to 200. So my question is, everybody calculate 100 parallel to 200. Everybody please calculate that equivalent resistance, if you would, please. 100 parallel to 200, 100 reciprocal plus 200 reciprocal equals engineering. This calculates to be what value, Javier?
66.67
66.67 ohms. Cool. And now, because I have a simple series circuit, do I have enough information to calculate an R total? People.
Yes.
And my R total works out to be what value, Abbas?
It works out to be 366.67 ohms.
Good job. And simply add the two. 366.67 ohms. Do I now have enough information to be able to calculate the current that runs through here? Remember, electrons flow which way? Out of the negative side, so they flow up, they flow this way, down this way, and like so. Do I have enough information to calculate an I total? How would I calculate an I total in this exercise? Question goes to, let's take a look here. Ryan, help us out here.
You would divide 7 volts by 366.67 ohms.
And that calculates to be what value of current, my friend?
I got 19.09 milliamps.
19.09 milliamps. Does everybody concur that we have 19.09 milliamps? And you do these calculations more than once to feel really good about them. So let's go ahead. We have enough information to do the second table. Remember, for R1, for R2, R3, totals. We want I, we want direction, and we only want an R total. And the R total worked out to be right here, R total 366.67 ohms. And we have what for a total voltage here? 7 volts. We had enough information, 7 volts. We had enough information to be able to calculate a total current. And so my total current, we are happy with 19.09 milliamps. Everybody okay with that? Don't need this. So what do we do with that? Where do we go from here based on what we've done before? Who can give me a breadcrumb trail as to where we go from here? Erica, can you tell us where we go from here?
Sorry, can you repeat the question again?
Yeah. So we have a simple series circuit, and based on the simple series circuit, we were able to determine ohms total, I total. Once we have the I total, we fill this into our little table. Where do we go from here is my question.
Put the current for resistor 1, which would be the same as the total.
Is it resistor 1?
Not resistor 1, resistor 3.
Precisely. In this simple series circuit, which derived from here, R1 and R2 were in parallel. They became this green resistor equivalent 1. This is an original resistor. The R3 sat here all the time. And as this current of 19.09 milliamps flows in this simple series circuit, it flows through this original resistor. And this original resistor is R3. So are we clear that this 19.09 milliamps flows through one of the original resistors, which is R3? And if we're good with that, in this simple series circuit, we can write that value here, 19.09 milliamps. And which way does it flow? Up, down, left, or right, Erica, through R3?
Left.
To the left. So I draw an arrow to the left. Is everybody okay with, and we're done with the simple series circuit, we're clear that current flows through to the left based on electrons leaving this plate and forcing it to go this way, and the current's going to be 19.09. Any questions at this point? Where do we go from here? What would be the next step of what we would do? Abbas, what would we do next?
The next step is you would go back and you would figure out current for R2 and R1 by using that formula.
By using which formula?
Current divider formula, I think.
Current divider formula. Okay, so we have to take, in other words, what Abbas is saying, we have to take this information and now bring it up to this circuit. And as we bring the information up to this circuit, the return current is 19.09 milliamps. The outbound current that flows through R1 is 19.09 milliamps. Remember, what goes out of the source is what comes back. But what happens when this current flows here and hits node A? It splits. So part of the current goes in this direction, right? Goes in this direction, and then it's forced to go down. Does this reveal, this circuit here reveal, which are my arrows for R1 and R2? Can we clearly see that R1 flows to the left? Draw it to the left. Can we clearly see that the current through R1 flows downwards? Draw down. Are we good with these directions in filling in? So far, so good? Tawan, what do we do next, pal? Tawan, take off your mic. So we can
find the R1 current.
Yes. We want to find our currents going through R1 and R2. What method would we use to find the currents going through R1 and R2?
Ohm law.
Well, Ohm's law means I need a voltage. Do I have a voltage?
We could go, can we help?
Tawan's not wrong. We can do this using Ohm's law. Let's use a slightly different approach. For the first step one, we used current divider. I'm going to follow Tawan's suggestion. Well, suppose we want to try to use Ohm's law. Ohm's law says we need, for Ohm's law, V, I, and R, don't we? We need a VIR. So far we haven't talked about voltages outside of the source, but check this out. Do I know the voltage between A and B?
Yes.
How can I find the voltage between A and B? Isn't the voltage, what is my resistance between A and B? Isn't my resistance between A and B the 66.67 ohms? Wasn't it 100 parallel 200? This is 66.67 ohms. Are we in agreement that green resistor is 66.67 ohms? Yes? Are we also in agreement that we have a current of 19.09 milliamps flowing through it? Do I have my R? Do I have my I? Can I use R times I to calculate a voltage between A and B? The answer is yes. So my VAB is equal to VREQ1 is equal to 19 IR. Okay, that's what it's equal to. I times R. That's equal to 19.09 milliamps times 66.67 ohms. Everybody do that. This current that we calculated times these ohms that we calculated previously. So 19.09 milli times 66.67. I like this because we can always use more than one approach. We've been using current divider, but we're not stuck using current divider. So I'm going to do this with you. 19.09 exponent, oops, I did it too fast. Dyslexia. 19.09 exponent negative 3. There's my milli. And I'm going to multiply this by 66.67. Did I type that in too fast? No, I didn't. And so this calculates to be what value? Tawan, do you have a voltage for me?
I got 1.3 volt.
I want 2 digits after the decimal point, my friend.
1.27.
Okay. Since the first week we were together, we're not going to round and we're not going to put down 1.3. You put down 1.3. This is going to be bad. 1.27 volts. Is everybody okay with that? Pretty straightforward. So far, so good. Well, guess what, my friends? If that's 1.27 volts between A and B, isn't that 1.27 volts across R1 and R2? Because these two guys are in parallel. This is VR1. This is VR2 because they're in parallel. Do I know the V across R1? Do I know the ohms of R1? Can I take this V, divide by these ohms to find this current? Ohm's law, as Tawan suggested. And the answer is yes, we can certainly solve this, not just with current divider as we did before, we can certainly solve this using Ohm's law. Nothing wrong
Can
with
we use also Kirchhoff's voltage law here?
that. Not yet. Not yet, hold that off. We're gonna save that for a proof. Okay, okay. So yeah, Kirchhoff's voltage law compels us to do a subtraction method, and we're not gonna deal with that right now. So let's stay with Ohm's law. We're okay with 1.27 volts as being the voltage across R1 and R2. So if I want IR1, isn't that equal to 1.27 volts divided by 100 ohms? Everybody do that. 1.27 divide by 100. And you end up with
12.7 milliamp.
excellent, 12.7 milliamps. And now, if I want IR2, isn't that the same 1.27 volts? And now divide by 200. And what does that calculate to be? Simply divide the previous one in half, and you end up with
6.35 milliamps.
6.35 milliamps. So this is a different approach of finding these currents. We're using Ohm's law to find these currents. In the first approach, we used current divider to find these currents. So now let's highlight what it is we need from both of these tables. Here, 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 and here. Yes? Okay. Now, can I, with the very last step, I can transfer this information on this piece of paper if I wanted to, but since I have it all written here, I'm just going to do the last step. The last step in this exercise says, what are we going to do is we're going to algebraically add the currents and voltages from the two tables above. Step 1 and step 2. Here's my step 1 table. Here's my step 2 table. Let me bring this a little higher so it gets a little more distance so we can see more of this. Focus. Cool. All right. Here's my step 1 table. Here's my step 2 table. And I want to fill in the algebraic sum of these two. So looking at the current through R1, here's R1. What was the direction of current through R1 and from step 1? It was to the left. Look at the current from step 2. From step 2, the current was to the left. Hey, both of these are going in the same direction, yeah? If they're both going in the same direction, am I going to use subtraction or am I going to use addition?
Addition.
Yeah, if they're going in the same direction, they're not antagonizing each other, you're going to add them. So does this also help tell us the final direction of current through R1? The final direction of current is to the left, right there. And I'm going to add the two currents together. So let's go ahead and add 54.55 plus the 12.7. So 54.55 plus the 12.7. And we end up with how many milliamps in total? Question goes to Tony.
67.25 milliamp.
67.25 milliamps. Is everybody okay with the final table having through R1 a 67.25 milliamps and a final current is flowing to the right? Any questions on how those numbers came about? Those numbers come from the two separate tables we got before. This current through IR1 flows to the left. This current through IR1 also flows to the left. Therefore, you add the two currents together and we end up with 67.25 milliamps flowing to the left. We're done with R1. Let's go ahead. While we have that number on our calculator, while it is here, do we have enough information to calculate the voltage? Because the value of R1 wasn't the value of R1 100 ohms. So can I multiply these two numbers together? Take this number, while it's fresh on your calculator, can I just multiply that by 100 right now? Times 100. Since it's on my calculator, I don't have to key it in later. I'm just going to do the math now. So if I multiply this by 100, Jess, what do you get?
600 or 6,000. I didn't put it in engineering, sorry. I'm still trying to put that into my calculator. Again.
Yeah, I know. You've got it on the tip of your tongue, too. It works out to be 6.725 volts, which is 6.73 volts. Is what I mean? Yeah, 6.73 volts. Are we good with that?
Yeah.
Okay. Is everybody all right? Since we happen to have this current, let's just go ahead and just jam that voltage in there. It's pretty fast. Okay, next current for the next resistor, R2. So take a look at it. So from the first table, what do we have? From the first table, current's going up for R2. From the second table, the current is going down. Uh-oh. This one's going up. This one's going down for R2. Are we going to add or are we going to subtract? Subtract. Might is right. The bigger current will subtract the smaller current. The bigger current is my remaining current. So since 32.73 is the larger current in comparison to 6.35, what is the final direction of current through R2? Is it going to be up or is it going to be down? Harpreet?
Up. Up.
Up because that's
because it's a bigger number.
Bigger number. Everybody okay with the final direction of R2 going up? And let's go ahead and subtract bigger number minus smaller number. So let's clear the calculator, key that in. 32.73 exponent negative 3. And subtract 6.35 exponent negative 3. Then hit equals and hit engineering. When you go to do so, you end up with what number, Ephraim?
I have a 26.38.
And it is 26.38 milliamps.
Correct.
Everybody okay with that? What was the ohms of the second resistor? 200 ohms. And so while we have this number on a calculator right now, could we quickly calculate the voltage?
Yeah, that's 5.23.
Times 200. And you're right, this works out to be 5.2 what?
I have 3. Oh, sorry, 2.8. Sorry, 2.8. My bad.
You're killing me.
Sorry about that.
No, you're being, you do a you know, I would see one thing and read something else. It slips from that's just me anyway. All right, the last resistor, 300 ohms. All right, my friends, let's look at this. Last resistor in the first table has it going to the left. In the second table has it going to the left. Guess what the final direction of current's going to be? To the left. Does that make sense? If this is to the left and this is to the left, then the final current's going to be to the left. Are we good? So far, so good. Cool. So what do we do with these currents? Are we going to add or are we going to subtract here, my friends?
Add.
Add.
Add them. So with your calculator, clear 21.82 exponent negative 3 plus 19.09 exponent negative 3 equals engineering. Tony, what do you get?
I have 40.91 milliamp.
40.91 milliamps is correct, and the directions to the left. And while this number is on the display of your calculator, what should we do?
Times 300.
Times 300 to get the voltage. So times 300. Boom. What voltage do you get?
12.27 volt.
12.27 volts. Is everybody okay with these final numbers on this table? While we have these numbers on this final table, you are asked, and I give you a nice big circuit here for you to do the reconciliation and Kirchhoff's voltage law to do this particular page. What are we going to do is this. We're going to redraw the original schematic that we had. The original schematic, I'm going to do this large. Come up here, a resistor. Come up here, here is A. Come up here, here is point B to ground. Come over to here, and here is another resistor. And here's this. The S2, 7 volts. The S1, 12 volts. And we're going to label some additional points here. The additional points will be, this will be point C, this will be point D, this will be point E, and this will be point F. Just put little points here, all right? In our redraw, if you're not given something really nice like this, it's already drawn for you, in your redraw, we don't have to label the ohms, but we do have to label the voltages. So what is my VR1? My VR1 from my summary table, 6.73 volts. 6.73 volts. What is my VR2? VR2, 5.28 volts. What is my VR3? R3 is 12.27 volts. Can we just write the voltage values right on the schematic? So far, so good? Then what you need to do, you have to polarize these components. So the voltage source here is negative on top, positive on the bottom. This one is positive on top and negative on the bottom. Now you have to bring in the arrows that show direction of current flow. Well, we have that arrows come from our nice handy table right here. And let's go ahead and fill this information in. The current through R1 is which direction? To the left. So I must put it on the circuit flowing to the left. Do I have an arrow flowing to the left? Yeah. The current through R2 we reconciled as going up. So I'm going to draw this guy going up. Now do I have an arrow going up? And then the current through R3 is also flowing to the left. So I'm going to draw this flowing to the left. Right there. So I polarize my sources based on their plates. I bring in the arrows based on my table. There's one more thing I need to do. I have to polarize my resistors. How do I know the polarity across these resistors? Well, electron current model flows from negative side of device through it, comma, there's a comma, through it, comma, to the positive side. We got this from week 1. Okay, that definition came from week 1. So with this information, can I polarize R1? What is the polarity on the input side of the electrons and where they exit? The electrons are entering the right. So they flow from the what side? Negative side of the device, then through it to exit where? The positive side. So that being said, this side of R1 should be what polarity, Jess? Based on this definition. This side of R1, the input side of R1, where the electron will be negative, precisely. And the exit side will be positive. Are we good with the marking the polarity based on the definition, which is guided by the direction of the arrow? So far, so good. Everybody okay with polarity on R1? How about R2? The current enters, the electrons enter the bottom and flow out the top. So the entry point for electrons should be what polarity here, a boss at the bottom?
It should be negative.
It flows into the negative side and out the positive side. So it must be negative down here and positive here. Good job. And one more, R3. It's going in the right-hand side, out the left-hand side. So the input side, Tony, what polarity on the input side?
R3?
R3. This side.
Oh, that's a negative.
Will be negative on this side is correct, and positive on this side over here. So far, so good? Okay. So now we're going to use something. Here's where Kirchhoff's voltage law will come in, KVL. And KVL, I give you a very nice definition on the handout. And KVL says, right here, that KVL, Kirchhoff's voltage law, says the algebraic sum of voltages in any closed loop must add up to be how many volts? 0 volts. That's a law, like Ohm's law, like Watt's law. It's absolute. It's irrefutable. Any closed loop, the algebraic sum must add up to be 0 volts. So I give you a loop sequence. I give you a very specific loop sequence to follow. So when you follow this loop sequence, CABFC, so let's go ahead and do that. Loop CABFC. when you follow that particular loop, let's go ahead and see what we do, how we reconcile this on the circuit. You want to start at C, and then you go to A, then you go to B, then you go to F, then you go back up to C. Can everybody see this loop that I'm pointing to with my finger? So starting at point C, what is the very first thing we encounter when we go from C to A? My friends, what's the first polarity we see?
Positive.
Okay, so you have a positive, what value?
6.73 volt.
So a positive 6.73 volts. And then we're at A, so now we have to go from A to B. So from A going to B, the red probe sees what polarity?
Positive.
What value of voltage?
5.28 volt.
So we're going to add that to a positive 5.28 volts. Now we're at point B. Between B and F, is there anything to add or subtract? Nothing on that wire. Now we're at F and we want to go back to C. So at F, as we go back up to C, what polarity do we encounter?
Negative 12 volt.
We have to add a negative 12.00 volts. And when you go to do so, does this add up to be 0 volts? Well, you end up with a 0.01. That's essentially 0 volts. And the only reason why we have a 0.01 difference is because why? We're rounding, we have rounded numbers. But is this close enough to 0 that we could say we have 0? I'm sorry, you can't see that. Is this close enough to 0 that we can say we have 0?
Yes.
Yeah. Is Kirchhoff happy with the first loop? Hope so. Now let's see what happens with the second loop. So the second loop is here. Loop A, D, E, B, A. So with this particular loop, let's examine the circuit. We're going from A to D to E, B, A. A, D, E, B, A. A, D, E, B, A. So as we go from A to D, what's the first thing we encounter going from A to D? A what?
Positive 12.27 volt.
We have a positive 12.27 volts. And then now we're at D going down to E. What's the next thing we encounter?
A negative 7 volt.
Okay, so we're going to add a negative 7.00 volts. What's the next thing we're going to add? 0 here, so I don't have to write it down. And then from here, B back up to A, what do we see?
We got another negative 5.28.
So we had a negative 5.28 volts. And when we go to add this up, guess what, my friends? We're going to end up with a 0.01 volt difference again. And that's essentially 0 volts, yes? I didn't write that correctly. This is essentially 0 volts. Is Kirchhoff happy with the second loop? There's one more loop to do, and that's the big loop going around the outside. And I'm going to call that out as loop CAD-EBFC. That's a whole bunch of points. I'm going to start where? I'm going to start at C, go to A, go to D, to E, B, F, back up to C. So this is the outside loop. Initially, we did this little loop on the left. Second column, we did the loop on the right. But if Kirchhoff is a law and our numbers are correct, we should be able to add the loop on the outside, and it should algebraically add to be 0. Let's see if we can make that happen. So from C to A, we encounter a what? Positive
6.73.
So positive 6.73 volts. Now we're at A. A, we want to go towards D. We encounter a what? Positive 12.27. So we're going to add positive 12.27 volts. And now we're going to encounter a what?
Negative 7 volt.
So we're still adding, but we're adding now a negative 7.00 volts. Now we're at E. So the path is from E to B to F. Is there anything to reconcile at the bottom of the circuit? They're all zeros. I don't even have to write them down. Now I'm on my way back up. What do I encounter?
Negative 12 volt.
So I'm going to add a negative 12.00 volts. When I go through the outside loop, guess what? I'm going to end up with 0 volts.
0.
End up with 0. So does everybody see we out of all these numbers, we end up with a 0. And so in each loop has Kirchhoff's voltage law substantiated through adding them up to be 0 volts, that our numbers here must be correct. That way your final chart is correct. And that, my friends, is how you reconcile superposition. The exercise is actually a lot faster than I described, but we took a lot of time in explaining in great detail the 2 different steps. So what did we do to recap? When you're faced with superposition, you have an original circuit and you're asked to produce final VIRs, 2 voltage sources. So what do? First step, replace VS2 with a wire, solve for currents and directions. It means you have to redraw. You have to simplify this ultimately down to a single resistor, RT, find IT, solve for currents and directions. Step 1. Then what do? Step 2 is you have to return VS2, replace VS1 with the wire, and solve for currents and directions. So VS1 has been replaced with a wire, VS2 has returned. You solve from this direction, ultimately to a single R total, I total, and you solve for currents and directions, which you have. Then what do? Then you combine your data between your 2 tables. Between these 2 tables, you combine your data into a single table, and we did, and the single table allowed us to determine final directions. In some instances we added, some instances we subtracted, based on whether the currents were same direction or opposite direction. Final currents, final voltages, transfer that information to a nice, roomy, spacious, page-sized circuit. Gives you plenty of space to mark your arrows for directions, give you plenty of space to write down the voltage values right here, gives you plenty of space to mark the polarities. Then you go through Kirchhoff's voltage law with your 3 loops and confirm they add up to 0. That, my friends, is superposition.